All right, so now we're going to move on to a couple of the other big concepts in calculus aside from convergence and the limit. First, the derivative, and second, the integral, the Riemann integral. The definition of the derivative invokes the definition of limit, invokes the limit at any rate. So if we look at it correctly, we should see these same pictures popping up, whether or not they typically pop up in the literature. So what I'm going to do is say take the squaring function, old friend, nice differentiable function, and think about what we mean when we talk about the derivative of that function at 1. The first remark is you see the graph as usual with the domain and codomain. Less of an issue than the fact that I put the slopes off there on the side so we see numerically what the slopes are. And again, to stress this point again, the key thing is slopes, plural. Not a slope. Not a slope between 1, 1 and a point nearby squeezing towards it, but all of the slopes between 1, 1 and the points, plural, 1, 1, and the points nearby on the graph. So, if you can visualize it, limit, x goes to 1 plus minus of, f of x minus f of 1 over x minus 1 or something. Here's the picture of what's going on there. The 1 plus minus in the domain is here. The relevant points on the graph are in purple. The slopes between your point of interest, 1, and all those other points form these two blue wedges. And here's the slopes that you get. I just want to quickly show convergence. There's not a lot to show in this animation. But if you draw it correctly, what happens? Well, you squeeze the 1 plus minus dot, as it does, squeeze closer and closer to 1, and simply observe what happens to the slopes. What you see is the slopes converging to 2. So, of course, the derivative equals 2, which, again, as a limit is a bit of a lie. The slopes are squeezing toward 2. There's a sort of a 2 plus minus dot going on here. The further we zoom in, the closer they squeeze. That is convergence to 2. That's why the derivative of this function at 1 is 2. But it's not just the slopes that exist that work here. Everything works, and in fact, especially in the divergent cases where there's less good stuff to say, you can say something good. You may say the slope of the square root function at 0, maybe the right slope, is infinity. Or it's vertical. I don't know, vertical slope doesn't make any sense. But the slope is infinity. Well, let's see the infinity. We've seen, I've said that every infinity you ever see in calculus looks like this infinity object we've drawn. What happens if you do play that same slope game near 0, 0, only going to the right because there is no function to the left? Well, as you squeeze closer and closer to 0 from the right, these slopes, plural, all of the slopes between that point and the nearby points, squeeze as larger and larger and larger and larger, kind of slowly, larger and larger and larger and larger numbers. That was our very definition of what plus infinity looks like. That's an infinite slope straight from the definition. Okay? Well, that's not so interesting. Differentiable functions, pi over 2. You can see this in all the cases. The further you squeeze in, the closer the slopes, plural, get to 0. Even for something, though, like a discontinuous function, the function is not differentiable there, but you can still make sense of this quotient of this limit of slopes, if you like. If you try and do the definition of derivative, what you see is this mess. You take the 0.22 in this case, and the slope between that and all the points nearby. And then you let the 2 plus minus squeeze, and what happens to the slopes? Well, because both jumps are upward, you actually see another infinity. This is another infinite slope situation, if you like. Of course, it's a non-differentiable function, but the way in which it's non-differentiable is specifically this same infinite slope, in some sense, as the square root function. Moving forward from that, the Riemann integral for this second little half here. The standard definition of the Riemann integral is in terms of limits again. It's the limit as the mesh of the partition goes to 0 of the Riemann sums, all the Riemann sums that are possible for partitions of that mesh. So what you do is you have a function, you partition the interval in some way, you take sampling points, you form a Riemann sum, and take a limit. Well, more or less. If we draw this out, let me give you a nicer function here. Here's the square root function on some interval. The axis down there at the bottom is to plot the Riemann sums. I haven't given you an x or y axis on this graph. I'm just illustrating the concept. What the definition says is take your interval of integration. I'm trying to integrate over this dark part of the curve. Choose a partition, choose sampling points, and form a Riemann sum, and I've plotted the Riemann sum. Notice the x says Riemann sums, because you don't get convergence without plurality in some sense, and everything involves this plurality. What the definition really says is Say your meshes are up to 1.5. This is the 0 plus in the limit as the mesh goes to 0 plus. Suppose your meshes are allowed to go up to 1.5. Look at every possible partition and every possible Riemann sum that thereby comes out, and look at those Riemann sums plural. Well, of course, we can only do this kind of in a Monte Carlo method because there's way too many partitions and possible sampling points to bother computing them all. But this is more or less what it looks like. What does the definition then say? Well, what happens when my partitions are only up to, say, half a unit in mesh? Only look at those partitions, restrict your focus. What happens to the Riemann sums? Well, they squeeze down a bit farther. And what happens if I only restrict myself to partitions of mesh, say, less than a quarter? They squeeze even further still. On this axis where I'm plotting the Riemann sums is specifically this convergence that's happening in the definition, seeing very clearly. We see one of these plus minus dot situations. And again, the meshes converging to 0, the 0 plus underneath the limit, and the values converging to some number are exactly the same in all the other cases. So that's a quick look at the derivative and integral just to put things in context for the rest of Calc 1.